Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss a new topic of unit number 6 and the title of it is eccentrically loaded column and we are going to consider a biaxial condition. In the last lecture, we have discussed about the eccentric load and eccentricity, the concept of eccentric load and the eccentricity, okay, and based on that we have considered a uniaxial condition. So the uniaxial means whatever the load we have applied, it is eccentric about one axis only. It may be a y-axis, it may be a x-axis, okay. So this is the case of uniaxial condition. Now in today's lecture we are going to consider biaxial condition. So it means that we have the eccentricity about x-axis also, about y-axis also, therefore it is known as a biaxial condition, okay. Therefore we have a figure, okay. This is the cross section of a column, a rectangular cross section, okay. It is ABCD which has a width B and depth D. We have a rectangular cross section of the column ABCD which has a width B and depth D, and this is the x axis of that particular column and this is the y axis of the column, okay. And if you observe it carefully, a load is applied over here, a load is applied at this particular point, okay. So this particular load P is eccentric about both the axes, that is x axis also and about y axis also, okay. Therefore about x axis it is eccentric by an amount of ex, it is eccentric by an amount of ex, okay, and from y axis it is eccentric by an amount of ey, it is eccentric by an amount of ey, okay. Therefore we can say that a load P is acting by an eccentricity of two amount ex and ey, so it is a condition of biaxial state, okay. Therefore we will discuss this particular biaxial condition in detail. Therefore from figure, consider a column which is subjected with a eccentric load with respect to x axis and y axis, okay. So I discussed earlier, we have the column which is subjected with the eccentric load, and that particular load P is eccentric about it is eccentric with respect to x axis also and y axis also, okay. Therefore P is nothing but it is the load with an eccentricity with respect to x axis and y axis. B is equal to width of the column cross section, D is equal to depth of the column cross section. Ex is nothing but it is the eccentricity of the load with respect to x axis, okay. Ey is the eccentricity of the load with respect to y axis, okay. Sigma D is nothing but it is the value of direct stress and it can be given by P by A, it can be given by P by A. Therefore area will be B by D because we have width B and depth D, therefore area will become B into D, okay. Therefore we have the value of direct stress P by B into D. Sigma Bx is nothing but it is the value of bending stress due to the eccentricity of the load with respect to x axis. Sigma y will be the it is the value of bending stress due to the eccentricity of the load with respect to y axis. In the same manner, we have mx is equal to moment of eccentric load about x axis, and it can be given by P into perpendicular distance from the centroid, that is Ex, because it is mx, okay. My is nothing but it is the moment of eccentric load about y axis, therefore it will become P into perpendicular distance from the centroid, okay, it will become P into Ey. Ix is nothing but it is the moment of inertia about x axis, okay, and as we have considered a rectangular cross section, therefore about Ix we have Bd cube by 12 is the moment of inertia. Iyy is the moment of inertia about y axis, therefore it is given by dB cube by 12, it is given by dB cube by 12, okay. The direct stress can be given by P by A, which is equal to P by P divided by B into D, okay. the bending stress due to the eccentricity of the load with respect to x axis. Now we are going to calculate the value of bending stress sigma bx, okay, with respect to x axis. So we are going to use the same formula, bending stress formula we are going to use, and that is given by mx upon I xx into y, m upon I into y. So in term of with respect to xx, it will become mx upon ixx into y. Okay, therefore you put the value of moment about xx, it will become p into ax. Okay, divided by ixx will be bd cube by 12, ixx will be bd cube by 12, and the value of y, the value of y will become d by 2 plus minus d by 2, minus d by 2 to plus d by 2. Okay, because this is the centroidal axis about xx, and the distance of extreme fiber will be d by 2. The distance of extreme fiber will be the d by 2 in this manner. Okay, so one we will consider it as a positive and the one we will consider it as a negative. Okay, so this is the value of sigma bx. In the same manner, we have the bending stress due to the eccentricity of the load with respect to yy also. Okay, so sigma by is equal to my upon iyy into x. Okay, therefore we have the final equation p into ey upon iyy into x. Okay, where iyy is nothing but db cube by 12. Now it is the moment of inertia about y axis, and the value of x is minus b by 2 to plus b by 2 along this direction, minus b by 2 to plus b by 2. Okay, so once we have the value of direct stress, once we have the value of bending stress about x axis, bending stress about y axis, we will easily find out the value of resultant stress also. We can easily find out the value of resultant stress. So it is given by sigma r is equal to sigma d plus minus sigma bx plus minus sigma by. Remember that sigma d, it is always positive because it is direct stress. It is a value of direct stress, whereas sigma bx will be plus minus because it may produce compressive stress in one fiber and tensile stress in one fiber. So depending upon the sign convention, we have considered a plus minus sign. Okay, and same for the sigma by also. Okay, now from this equation again we will draw one conclusion, and it can be given by, let us determine the resultant stress at each point. Let us determine the value of resultant stress at each point. Okay, therefore we will concentrate on point A. First of all, we will concentrate on point A, and the resultant stress can be given by, from figure we have value of coordinate x and y negative, and hence the resultant stress will be minimum at this point A. Okay, therefore what does it mean? This is the x axis, this is the value of y axis. Okay, this is negative, this is negative, this is positive, this is positive. Okay, so we have the coordinate plus plus, after that minus plus, again minus minus, and plus minus. Okay, so depending upon those coordinate, if we concentrate on point, if we concentrate on point A, if you concentrate on point A, so point A lies in minus x coordinate and minus y coordinate. This particular point A, it lies in minus value of x and minus value of y. Therefore, from figure we have the value of coordinate x and y negative, and hence the resultant stress will be minimum at point A. Okay, now we will move to the point B. For point B, from the figure we have value of coordinate x as a positive and the value of coordinate y as a negative, and hence the resultant stress can be given by, sigma r about B will be equal to sigma d plus sigma bx minus sigma by, because if you concentrate on point B, for the point B, this particular point, for this particular point B, the x coordinate is positive whereas the y coordinate is negative. Okay, Therefore we will have this particular value sigma d plus sigma bx minus sigma by. Okay, now we will move to the point C. From the figure, we have the value of coordinate x and y as a positive, and hence the resultant stress will be maximum at this point, because as all the values are positive, so we will have the value of maximum resultant stress at point C. Okay, because x is also positive and y is also positive. Okay, so in this manner at point C we will have the maximum value of resultant stress, whereas at point A we will have the minimum value of resultant stress. Okay, now we will concentrate on point D also. From figure we have value of coordinate x as a negative and value of coordinate y as a positive, and hence the resultant stress can be given by sigma r. Actually it is not b, it is d, okay, which is equal to sigma d minus sigma bx plus sigma by, because we have x as a negative at point D, and y as a positive at point D. Okay, therefore the resultant stress can be given by in this manner. So in this way we will find out the value of resultant stress at each and every point for a biaxial state of condition. Okay, now in the next lecture we will discuss the concept of no tension condition for a column, and again we are going to concentrate on very important concept, that is core of section. Okay, so that we will discuss in next lecture. Today we will stop here. Thank you.